In this video, we're going to take a look at a theorem dealing with independent functions and what must be true. And then we are going to see how that theorem can play out in a couple different examples. Let's take a look at our theorem. So that y1 and y2 have this joint density function, f of y1 comma y2. That is positive if and only if our value of y1 is between a and b, and our value of y2 is between c and d for constants a, b, c, and d, and f of y1, y2 is equal to 0 otherwise. Then y1 and y2 are independent random variables if and only if that density function that we have there, this f of y1, y2, if and only if that can be written as a product of two other functions, g of y1, h of y2, where these functions, g of y1 is a non-negative function of y alone. Right? So it's a non-negative function of y alone, and h2 is a non-negative function of y2 alone. So if that can happen, if we can come up with these functions, g of y1, h of y2, where g of y1 is a non-negative function of y1 alone, and h of y2 is a non-negative function of y2 alone. If we can write f of y1, y2 as a product of those two things, then y1 and y2 end up being independent random variables. All right, so let's take a look at this in action in an example. All right, so here we have this example. Let y1 and y2 have a joint density function given by this, and we want to know, are y1 and y2, are they independent? And here we could define some function, g of y1, where g of y1 is equal to, we could say that it's 2y1 for 0 less than or equal to y1 less than or equal to 1, and it's 0 otherwise. We could say that h of y2 is equal to 3y2 squared for 0 less than or equal to y2 less than or equal to 1, and 0 otherwise. And then we can make the observation that if we were to multiply these two things together, that we do end up with f of y1, y2 is equal to g of y1 times h of y2. So y1 and y2, they are in fact independent random variables. Notice that g of y1, that thing right there, it is a non-negative function of y1 only. H of y2 is a non-negative function of y2 only. Right? And so that works out okay there. Excuse me, sorry. In our next example, we take a look at gasoline. Gasoline is to be stocked in a bulk tank at the beginning of each week and then sold to individual customers. Y1 is the proportion of the capacity of the bulk tank that is available after the tank is stocked at the beginning of the week. Y1 varies from week to week. Y2 is a proportion that's sold during that week. Y1 and y2 are both proportions, so they take on values of 0 to 1. However, that value of y2 cannot exceed the amount available. So it cannot exceed the value of y1. So our joint density is given by this thing, and we want to know are they independent? And this will feel like I'm going to hand wave a little bit, but I'm going to say no. The reason why these things are not, in fact, independent is because when we take a look at them, there are not values of A, B, C, and D with positive densities. Over the region. So these do not exist with positive densities over the region. So this value over the region with A less than or equal to y1 less than or equal to b, and C less than or equal to y2 less than or equal to d. So we don't have this existence of such a function, a non-negative function. So this is not, these are not independent. They are actually dependent. All right. Thanks, guys.